The last topic that we need to cover in terms of the bash shell is that of system management and process management, which are kind of one and the same. So to start off, we probably need to understand what a process is in the first place. And a process is basically anything on the computer that is owned by a single user that occupies one of three system resources. So number one would be CPU, so the central processing unit that does a lot of the arithmetic and calculations. Number two would be memory, so every program occupies some form of memory to execute its code. And then finally would be the I/O resources, which just means input and output. So in other words, if you had a USB or an external hard drive that is transferring data to and from your computer, that would be an example of an input-output device, and therefore would require those sorts of resources. So the goal of any computer or any operating system is to allocate these resources fairly and equally across different processes and keep the system running efficiently or as efficiently as possible. So that is kind of the job of the kernel, which is to take all these resources, look at their different priorities, and then assign resources to these processes so that they can run. Now there's a little tricky part to processes, and that is the fact that they're constantly doing this thing called a context switch. And that is where the kernel actually takes the resources that it's given a specific process and it kind of revokes those and gives it to another process or set of processes. And that's what a context switch is, and this is happening constantly over and over again when your computer is running. Now, of course, you don't see this, but this is happening, and this is why certain programs might slow down at times, is because maybe resources aren't being allocated to them. So to better understand these processes, we have to take a look at them behind the scenes. And on the screen here, you can see the basic method for creating a process. So when your computer starts up, it actually runs this thing called an init script. And on my machine, which is an Ubuntu distribution of Linux, that is called systemd, which is a initialization script that is stored in sbin. I'll just go over to the terminal here. It is actually stored in sbin, so if I actually need to put this little / there, and you can see I have this init script that is actually what we call systemd. And this is basically the script that starts the entire user space, which contains all of the programs and processes that a user can run and that applications run on. So this would be the number one process, and I'm going to show you. You won't know what this means, maybe you've seen it before, but we can type PS and then -P1 to show that this systemd is the process ID of 1. Now, of course, we haven't explained what this means yet, but I just wanted to show you that as a preliminary example. Now, once this systemd has started up, it basically spawns a bunch of other processes that can then spawn their own processes. So it's kind of like this whole parent-child relationship throughout the computer. On the screen, you can see how when we type in a specific command like ls into our bash terminal, this is actually an example of a process starting. ls is simply a program, and therefore it needs a process to run. So the ls command is the parent process, and what happens behind the scenes is basically this ls command will fork into two. So you have the parent and the copy of the parent, and then what happens is we actually execute the copy of the parent, which becomes the child process. And this is important because if we actually came into the terminal and we just typed exec ls, what's going to happen is this is going to completely destroy the terminal session. So I'm not going to actually click it or press enter, but if we typed that, it's going to kill the entire terminal session. You can try that out on your own. And that is why we need to first fork and then we execute the copy of the parent process. We can see this in action using the strace command. So let me get back to my terminal again, and we can type strace ls. And what this is going to do is execute the ls command and also give you the system calls that are going on behind the scenes. So when I press enter, you'll see tons of output, most of it that we don't actually care about. But I'll go to the top and show you what we just talked about on a system level. You can see that this is where we started our command, and the first thing that it does is this thing called exec.ve, which is kind of a sibling of the exec command, and you can type in, we can actually search this, so you say man exec.ve, and you can see that this is the execute program, and it's kind of in the family of all of these different exec system calls. So that is actually in the man pages, and if I go back one more time, you can see that it's a number 2 in the table of contents, which basically means that it's a system call. So if we go back up to the output, we can see that we have run this command, which will split this process or fork it and then execute it. And then what happens here is there's a bunch of different shared memory calls that are going on. That's what the M map is. And then we're reading something. And then at the bottom, you'll see the meat of the command, which can be understandable to us. So you can see that we are opening a read-only file, and then we are writing this to the terminal. And you can see all of the output is very plain English and is what is in my current directory. So if I typed ls, you can see that all of these folders are shown right here at the end of the command. And then finally you see that we exit with a 0 code, which means that it was successful. So this is the basics behind the scenes of creating a process and running that process. Now, another thing that we would want to understand about processes is, number one, how can we actually see the processes that are running on our computer? And then number two, we need to know how to kind of manage them. So if we type PS into the terminal, what we're going to see is the processes that are running within my terminal session here. So this is the terminal window, and you can see TTY shows which terminal we're in. So PTS /2 means that we're in the second window of the terminal. If we came over into this other terminal, we could type PS, and you're going to see that it's labeled number 3. So you can see that we have different terminals with different processes running in them. We can also type PSA, which will give us a little bit more info. This will show us all of the terminals that have processes and what processes are running in them. And then finally, we can type PSAX to get every process running on our computer. So as you can see, we're getting processes across the board, and this will go on for quite a while. Now, before we get into how we use this command in more detail, let's take a look at the difference between what we call a foreground and a background process. And to demonstrate this, I've created a little script called repeat, and we can cap the contents of this file out, and you can see that all this does is it waits 5 seconds and then echoes out that I'm an annoying script and I won't stop running. So this is going to get a little bit annoying, but bear with me. It will hopefully illustrate what a process is and how we can put it in the background or the foreground. So to start off, I will just run this command or this script, and you'll see that we're going to start getting some output that will run every 5 seconds. Now this is in the foreground, and as you can see, while it's in the foreground, I can't do anything. So if I typed a command, maybe I type clear and press enter, it's not going to do anything because this is actually occupying the terminal space and therefore I'm blocked from doing anything. I can also run this in the background, which means that I actually have control of the terminal while it's running. So to do that, I can use this little trick that applies to any program in the bash terminal, and I can type repeat, and then at the end I put this little ampersand that will tell it to go into the background. So when I press enter, you're going to see this little output that says the process ID, and then this thing right here is called the jobs number. We're going to get into both of these, but before doing so, you can see that this is actually still running. And you might say, well, you put it in the background, so why is it still running? Well, it actually is running in the background, but since we're printing to the terminal, we're still seeing it. As opposed to before, when we had it in the foreground, I can actually type clear and press enter, and it's going to clear output from the screen. But we're still going to get the output. So I can type anything I want. I can type ls, we're going to get an output from there. I can even cat out the contents of this file. But all the while, we are seeing this annoying little script that is still running in the background. Now, if we wanted to stop this script, we're going to have to understand something called a control signal. And before we do that, we'll have to take a look at process states because this will be integral into understanding the topic of control signals. So we're going to jump over into this clean terminal that's not actually getting that annoying output. And as you can see, this is just going to run into eternity, so no need to look at that forever. Now if we type PSA, we can see the repeat process that is running over in this other tab of the terminal. And you can see that right now it's actually sleeping, but we might be able to catch it when it's not sleeping. Let's see if we can do that. Probably not, but basically it's going to be alternating between sleeping and running. Now what is the difference between sleeping and running? And also what would be the difference between other process states? So if we go into the man pages for the PS command and we scroll down, I can actually maybe search for state, and we get process state codes. There are plenty of different state codes, but I'm going to point out maybe the most important ones that you need to know. So the first one would be R, which means that it is a running process. This is actively using resources of the computer. The next one would be S, which is interruptible sleep, which basically means that it is sleeping and waiting for something. So maybe it's writing to a file or opening a file, doing something that has blocking behavior. And so don't be deceived. When it says sleep, it actually could be running, but it's not actively consuming the resources. You'll also see T in just a second. This is what happens when we send a process signal to stop a process, and it's going to be put in the stopped state, or T. And then finally we have the Z for zombie process. And you'll see this every so often, but usually this is because we maybe brute force killed a specific process without kind of taking care of the child processes that this process had under it. So this you'll see every once in a while, and basically just means that it's still in the process registry, but it's not actually a running process, and it'll eventually kind of go away on its own. So if we exit out of here, you can see that when we run PSA, you're going to see some of these states. The little letters afterwards, don't worry about those. Those are not necessarily relevant. All we need to know is that this process and then these ones are all sleeping. We are running the PSA command, which is the one that we just ran, and the rest of them are sleeping. So if we wanted to come over to this terminal and stop this really annoying script that is running, we could do it using this other terminal by sending what we call a process signal. And to understand what these process signals are, we can use the kill command and type -L, which will print out all the signals that we can send to processes and the numbers that correspond to them. So the kill command is very versatile, and we can actually send different process signals by typing kill -S and then the process signal name. So that's one way of doing it. We could also use the number that it refers to. So I just type sig int, and that process signal is number 2. So I could just say -2, and then we'll give it the process ID to actually send that signal to the process. In our case, what we're going to do is send the stop signal to our little process that's going on over and over in this other terminal. So the first thing we'll need to do is figure out what the process ID is, which we can see here is 1531. After we have that, we can type kill -S, and then we're going to send it a process code called Sig TSTP, which is the equivalent of pressing Control-Z within the terminal that this process is running. So we can type Sig TSTP and give it the process number that we want to send it to. And when we send that, we're actually going to see that this has stopped. And when I type clear, we can actually see that it has stopped and it still has a job number of 1. So we can do something with that job number. We're not going to get to that quite yet. Let's go ahead and send it the continue, or Sig CONT signal. And when we send that, we're going to see that, oh boy, this annoying script has started all over again. So now let's take a look at how we might use jobs to place these processes in the foreground or the background. So we're going to send that Sig TSTP again, which will stop the process. And when we press clear, it's going to clear. And now we can type jobs and see that we have a job number of 1. So I can actually send a little command called foreground and give it a %1 to indicate job number 1. And what this is going to do is take this stopped process and throw it back into the foreground and start it again. So as you can see, it's done just that, and we once again have this script running again. So let's come back, give it another stop signal so that we can have it stopped again. And this time we can just run it in the background. So BG %1, and you're going to see that this is going to keep printing to the terminal, but this time we have it running in the background, and we have complete control of the terminal to do whatever we would like to do. But of course, it's going to continue to print out to the terminal. Okay, so knowing these process signals, you might be wondering, like, which ones are we going to use on the most frequent basis? And if we look at these again, typing kill -L, I'm going to point out just a few of them that you might be using on a regular basis. The first one would be sig int, which is the equivalent of Control-C, and just means that we are interrupting a process as gracefully as possible. Now, we also talked about the Control-Z signal, which will stop a process without actually interrupting and killing it. And that would be the number 20, or Sig TSTP. And this is the equivalent to Control-Z. Now, there will also be a few signals that you might use, including Sig Continue, which is what we use to resume execution of a process, and then Sig Stop, which is just almost equivalent to Sig TSTP. They're kind of interchangeable. I just wanted to point out that this one is the equivalent to Control-Z. And then finally, maybe the most powerful process signal that we need to know about is something called Sig Kill. And you'll see this a lot. It's kind of a hacky way to kill a process, and essentially when you run the task manager on like Windows or Mac or even Linux, when you press end task, that's usually going to be sending a Sig Kill signal. And what this is going to do is ungracefully shut down a process, and it's going to basically say, okay, Mr. Process, you're stopping no matter what. I'm not going to give you any time to clean up. You're gone. And so basically, this can cause some problems when we kill processes this way, but is definitely a last resort if something is just completely unresponsive. By now, you probably have a better understanding of what processes are. And so now I'm going to take you through a couple commands that we can run, or not really commands, but they're actually programs that we can run to get more information about the processes running on our computer, and therefore we can actually start to see the system performance of our computer and start diagnosing different problems that we might face. So the first command that we're going to talk about is the PS command. You've seen me use it a couple times, and you've seen me use the PSA, PSAX, and actually PS-P1, which is just signifying a specific process. Now there's plenty more things that you can do with PS, and I wanted to just take you through a super quick crash course on the PS command. The reason that I'm not going to spend a whole lot of time on it is because we have another command or program that we're going to use called top, which actually gives us a little bit more information, is a little bit more user-friendly, and it's my preferred program for diagnosing different pieces of your system. So we covered the PS, which prints everything in the current terminal. PSA is everything in all terminals, and PSAX is all processes on the entire computer. You can also type PS-P to signify a specific process. So again, we could type 1 for systemd, or what we could do, another way of doing this is typing PSAX and then piping that into grep and searching for a specific name. And you're going to see that by searching for systemd, we get this process number 1 and actually several more processes that are related to it. So that would be the basic usage of the PS command. I'm not going to get too much further. Obviously, the man pages has plenty for you to look through and gives you some examples right here at the beginning that kind of just give you a quick start. Now what I really want to talk about is something called the top command. And this command is super powerful. It's actually a whole program in and of itself. And I'll be taking you through how to use it. So when we type top into the terminal, you're going to see that we get a bunch of dynamic output. This output right here at the beginning is going to give us information about all of the processes that are running below this little white bar with the different columns and headers. The first row here is not all that useful to us, just gives us the time of day, how long we've used the top program, and some load averages. The second row is going to tell us how many processes we have running and how many are in certain different states. And we get to the third row, which starts to give us some useful information. You can see that here in this row we have some percentages, and these percentages will tell us what types of processes are taking up what percentages of the CPU. So right here, let's start with the obvious ones. The 5.3 SY stands for system. So the system processes are going to take up about 5.7% of the CPU. Over here we have a pretty large number, and this is going to be the idle processes. And then on the right we have WA, which stands for wait time, or the input-output process. So if per se we have a transfer of data going on, so if I took from my local computer and transferred a video file onto an external hard drive, you would see these this WA or IO percentage kind of increase as that's happening. Now I left the US and the NI for last because they're a little bit tricky. Now this US stands for the the unniced user processes, and the NI stands for the niced user processes. So you might even wonder what I'm saying when I say niced. So if we come down to this little bar here, you can see the NI field, which stands for the nice value of a process. Now every process has some sort of priority, and you can set this in the user space via the nice value. Now this is a little bit counterintuitive because the lower the nice value, the higher the priority of the task or the process. So it ranges from -20 all the way to 20, and so a -20 would have the highest priority of all nice values. So that's kind of what these user processes are, and I believe how this is kind of set up is if it doesn't have a nice value, then it's going to be over here, and if it does have a nice value, it'll be over here. So if you just add these two together, that's going to give you your entire user space processes. Okay, so we come down to the last two lines, which would be the memory lines. And you can see we have memory and swap. If you're not familiar, swap memory is just going to be that kind of reserve space. Think of a car with, reserve tank of fuel. That's kind of what swap space is for a computer. And therefore, there's an inverse correlation between the memory and the swap space. As the computer increases the utilization of resources, or it kind of gets overclocked, this might be happening. Maybe you're doing some video editing and you've got a browser open with a video playing and all sorts of things going on your computer. You're going to notice a slowdown in how fast your computer runs, especially if it doesn't have a whole lot of RAM, which would be the memory we're talking about here. So as we see in the memory section, and by the way, this is in kibibits or kibibytes of memory. You can read up on that. It's just a different measurement of bytes. It's different from kilobytes, so don't get that confused. But anyways, you're going to see an inverse correlation here between the two. So as we can see, here's the total values of each, and as we go over, we can see that we have this much, this many kibibytes, or about 3 million kibibytes of real memory free on our system, and that means that we have not really overutilized the resources. And this also indicates from the 0 we see here in the swap space, we have 0 swap used, which means that we have memory free, and so therefore we don't need to use any swap space. But as this value kind of goes down, we might start to see this value tick up, which means that we're overutilizing our computer, and therefore the performance is going to be degraded. That's just a basic overview of the summary, and if you have less processes, as I'm going to show you a little bit later down in this lower section, these numbers are only going to reflect what is below. You can kind of scroll down using the up and down keys, and as you can see, as I press the down key, these little scroll coordinates are changing. And by default on your top program, you're probably not going to see these scroll coordinates. The way that you will get these is by typing uppercase C. And since I typed it, it's going to toggle it off, but I can press it again, uppercase C, to put those scroll coordinates on. This brings us into kind of an explanation of how we interact with the top program. We can actually type in user input to the program, and it will help us to customize what we're seeing. The first one that I'm going to show you is the question mark. So if you type question mark, so hold shift and type that question mark like normal, it's going to open up this little help menu. And you'll see that there's a cheat sheet with all sorts of ways that you can interact with the top program. Now, it's a little bit intimidating, so I'm going to take you through some of the more common ways that we can interact with this program. So I press Q to exit out of that, and the first thing that I'm going to show you is how to set the interval of the top program. So I can press D, lowercase d, and I'm going to change this 3 seconds to, I don't know, 12 seconds. I press enter, and you're going to start to see that this display is not updating quite as fast. And that is because I changed the update interval to 12 seconds. It makes it a little bit more manageable for us. We don't have to constantly look at it changing. This is useful, and I generally will keep it a little bit above 3 seconds. Now, you can also manage processes within top. So if I wanted to maybe kill a process, I can do so by finding the process ID and typing kill. So, or not typing kill, but it's going to be, I believe, K. So I typed K, and then I'm going to enter a process ID to actually get rid of that process. So I'm scrolling through, and I don't see a process that I feel comfortable killing at this moment. So I'm going to go ahead and leave that, but if we wanted to, we could basically type in a process ID and then press enter to kill that. If you want to exit out of this little display here, just type some invalid process ID, and it's going to say unacceptable integer and exit out of that. So I haven't actually explained what all of these columns are. And before we get into modifying what these columns will say and what we get to see about our processes, we need to understand what we're seeing by default. So moving left to right, we start off with the process ID. This is pretty intuitive. We've seen what this is already. You are pretty familiar with it. We then have the user. So remember, each process is owned by a specific user, and therefore it's listed right here. We have a priority, which is basically going to give us the kernel priority of a specific process. And this is different from the nice value over here, but they are related. So the priority is actually equal to 20 plus the nice value. So I believe how this works is the priority is also going to work like the nice value. So the lower the number, the higher the priority. And so when we add these together, that's going to equal the actual priority of a specific process. So the PR, the priority, is going to take precedence over the nice value. But of course, we can use the nice value in the user space to influence the priority of a specific task. Alright, so we've got those two covered, PR and NI. Now let's look at these little memory things. You might actually have these in a little bit different order. I've kind of modified my display a little bit, but usually you'll see VIRT, or virtual memory, first. Then you will have res memory second, and SHR memory third. So the virtual memory is kind of all of the memory combined, and that's going to it's going to be made up of the res memory, which is the real memory that we're talking about. This is the stuff that we care about. And SHR is just a subset of res. It's not really that important to understand. So remember, res is what we're going to be looking at in terms of real memory. And so we're going to eventually kind of take out these unnecessary output of memory. Unless you're a systems admin, you don't really need it. Over here is going to be the process code, so this is the state of the given process. Over here is the percentage CPU that is used, pretty self-explanatory. And then percent memory is going to be this res value expressed as a percentage. And so this gives you basically how much real memory a process is taking up. The time is going to be the amount of time that the process has run, and then the command over here is what started the process. And going back to these kind of interactive codes that we can type into the top program, we can press lowercase c, and that's going to toggle the command into a different mode. So we can see the full path of the command by pressing C, and then we can go back to the abbreviated version by pressing C again. Okay, so what if you wanted to update this row right here to have different types of information? The way that we would do that is by typing lowercase f to enter the fields management window. Once we're in the fields management window, we just have a few ways that we can kind of arrange these fields. Now, the first thing that we need to know is these little stars on the left. So if you see these stars, this means that this is an active field in your current view. So as we saw, all of these are showing up in our top program, and therefore they have this little star. Now, if we wanted to remove one of these, we can type lowercase d. So if I wanted to get rid of virtual memory, I can press D. I might also press D on the SHR, and maybe even the priority, and that'll be just about it. We don't need to get rid of anything else. I guess we can get rid of the command because that takes up a little bit of space. Now, if we wanted to put in a new field, maybe I want to come all the way over here and pick up the environment variables. So this would represent the environment variables that are accessible to a particular process. What we can do is, you can see we've just got the short code highlighted, but if we press the right arrow key, that's going to highlight the entire field. Once we have this highlighted, we can press up and down arrow keys to move this throughout the menu. So you can see the environment little field is moving up, and we can bring this all the way up to the top, and I might put it after the user field. And to set this into place, I can just press enter, and that's going to deselect it and set that in place. The last thing I want to do is press D to activate this. You can see we got that little star there. And then finally, maybe we wanted to sort by something different. So maybe instead of CPU, we want to sort by memory. We can do that by pressing S. So I pressed lowercase s. You didn't see anything happen, but we're actually now sorting by memory. And we can see this when we press Q and go back into the top program. We can now view different fields within our top program, and you can see that this environment field is now sitting right after the user field. You can see all the environment variables available to this particular process. You can also see that we are sorting by memory, so the highest memory is on the top, and that cascades down in a descending order. So that would be how you edit the fields within the top program. Once you have customized all of your fields, you may want to save your configuration. The way that you will do this is by typing capital W into the top program. So when I press capital W, you can see that it quickly popped up a little alert message that said that I had written to my top RC file. So let me press Q to quit this program, clear the terminal, and what we're going to do is cat out the top RC file, which is located in my home directory. As you'll see, there's a little bit of gibberish in here, and obviously we are not going to be able to customize this as it is shown right here, but by typing that capital W, all this file contents is going to allow top to open up in the same configuration that we left it. So you see that we now have this environment kind of permanently there for our top program. Now I could also just delete, just echo an empty string into the top RC file, and then when I press top, it's going to say incompatible RC file, so we actually need to just delete it. Delete the top RC file, and then we are back to our original configuration right here. Okay, so the last thing that I wanted to show you is this, actually two things. Number one, you can also kind of filter things in top. So maybe we just wanted to see one particular process ID. Currently, when I'm recording this video, I'm using this OBS recorder, and it is process ID 560. Now maybe I wanted to see a little bit more about this process because clearly it is using a whole lot of CPU, over 100% of the CPU. So to kind of isolate this process, what I would do is type uppercase O, and this is going to ask me to add a filter. Now once I have typed uppercase O, I can say process ID equals 560 and press enter. And you're going to see that this actually registers anything that has 560 in it, so 2560, 15604, but you kind of get the point. We're filtering by a specific process ID, and we now have this little OBS here at the top, and we can get some more information about it. To clear the filter, we just press the equal sign, but we could also check the filters we have by typing lowercase o. Actually, no, that would add the filter. It would be, let's just type some gibberish in there, and we type Control O to see the filters that we have, and it shows that we have this one filter right here. We can clear it by pressing equal sign. Let me exit out of there and press equal sign, and you can see that we now have the original top configuration set. We can also go into alternate mode. So if we type capital A, it's going to give us this really weird configuration, and you can see that we have actually 4 menus that we can customize each one of them. So I can either type G followed by the number of the menu I want to go to. So if I wanted to go to 3, I'll just type 3, and you can see up in this top left corner I have the 3rd menu highlighted. And now if I went to maybe in fields management and started to turn some things off, maybe we'll just turn some random things off, you can see that down in field 3 here we have different menu items. So we can also navigate between them by typing A and W. This will just toggle between the different menus, so you can see up in this top left corner, as I press A and W, we're going between the different menus. So that's just a way that we can customize our top interface and give some more output in a smaller space. To round off our discussion on system management and process management, I have 3 more commands, 3 more bash commands that we can look at that are far less complex than top, but they will give you some quick information about your system. So the first one would be LSOF or LSOF, and this is going to be very useful, especially in networking, because we can see all of the open files on our computer. When I press this, press enter, you're going to see a mirage of output that's going to print all sorts of stuff, and these are all the open files that are on my computer right now that are either open by me or by some sort of process that has them open. So you might say this is pretty useless, we've got so much output, and how are we going to ever filter through this? Well, the way that we do this is by putting some arguments with the LSOF command. So maybe we wanted to see all of the files open by my user. I would type elseoff u Zach, and that's going to open all the files opened by my user. Still not super helpful, but you can kind of see if you maybe added that with the grep utility and searched for something in particular, that would narrow down your search. Another thing you could do is list all your network connections on your computer. So in a Unix-based operating system, everything is a file, and therefore things like pipes and sockets and network connections, they're all files. So we can type elseoff-I, and this is going to show us all of the network connections or networks that we have open on this computer. And you can start to see that we have some ports here, some IPv4 addresses, so on and so forth. Now, this is not super useful right off the bat, but maybe we wanted to search for every file open for a specific port, or in other words, what ports are open on our computer. And the way that we would do that is by typing elseoff-I and then maybe something like TCP22. And it's going to show that I don't have anything on port 22 right now, but if I did, it would actually show that as output in the terminal. And the last thing that you might want to do with the elseoff command is something like maybe we want to see the files that are still open for an external hard drive or something like that. So if I came over to, oh, we still have this script running, that's kind of funny. Let me go ahead and kill that real quick. So we want to kill brute force method, Sig Kill process, and we want to kill the 1531 process for the repeat. So we press enter. Alright, we got that killed, and now we can move on. Let me clear the screen here, and I will show you that if I go into my media and Zach and then my ZE2 external hard drive, this terminal is now utilizing that hard drive. And with the elseoff command, I can see that this is happening by typing elseoff.f and then two little dashes, and then I specify what this does right here is tells it that the next thing is going to be a mounted volume, and so then I give it the mounted volume that I want to look for, so it will be ZE2, and when I press enter, it's going to show me that this process ID 20398, is the one that is still using this particular hard drive, and that is why I cannot eject the hard drive. If I come back to this terminal and go back to my home directory and try this command again, we see that there's no output, and therefore I can successfully eject that hard drive. So that's just a basic overview of the elseoff command. You can find all of your open files. It's very useful in very practical in many cases, as we saw right there. Now the last two commands are more relating to system management. So we have the free command, which is going to kind of give us some basic information on our memory and our swap memory. So similar to the top command, where we have this little these lines right here telling us, we can just type in free to get that information really quickly. The last command that we have is the time command. So we can write this time command into the bash shell and give it some sort of program to run. So maybe instead of ls, we'll run the cat command. So maybe we wanted to see what's in this repeat script again. So we can type time cat repeat, which will give us the CPU seconds that it takes to execute the cat command and print out the contents of this file. So you can see we have actually printed out the contents, and it gives us some statistics here at the bottom. Now, why are these useful? Well, one reason these might be useful is because it gives you an idea of how much a process has to wait for system resources. Another good use for this, a lot of companies will actually use CPU seconds to bill their clients. So it's kind of just a neat thing to understand. So in order to understand this, we'll start with the real seconds. So this is telling us how much total time the process took. You can see it took 0.002 seconds. And then it's going to tell us the user time, which is how much time it took the actual code to run from that command. So this cat command is an executable. It runs a certain amount of code, and that code takes a certain amount of time to run. And that is what user time is. And then system time is how many CPU seconds it took to actually utilize system resources. So in this case, this command didn't run very long. We don't have an awesome depiction of this, but we can take these three metrics and get our total wait time for the command. So wait time is going to equal real minus user minus system. And that's going to give us the amount of time that this process was sitting around waiting for resources on the computer. So just a kind of a neat trick to see how efficient your commands are running. Maybe you have a process that's taking forever, and you can use this to identify whether it's just taking a long time to run the code or it's taking a long time to wait for system resources, which might indicate a performance issue on your computer. That is pretty much it for process and system management. I know this section was a little bit long, but hopefully it gave you more clarity into how your system works in terms of processes and how you might go about diagnosing it if it starts running slow.